Okay, I'm not sure everybody's going to get to see this in person, so I'm going to record the final exam review. It might take a few. This is part one, and it might take a few part ones to get up to part two. So I'm going to call this one part 1A, and we'll see how far we go. So we initially talked about physics and why we perfected the art of science, pulling from philosophy and other assorted things, and all the other, geology, biology, all those other things. We try and get at the root of what's happening. It's because we want to know why, right? We want to know why things are happening in certain situations. We can predict natural behavior, and I should put predict in quotes, right? Because we want to predict, we want to be able to say, oh, you know what, theoretically we should get this, and then when we do the experiment, sometimes we do get that, right? And it's because our assumptions or whatever were correct. So of course this is all to a degree, right? How good are our assumptions? How good are the assumptions made to get how good are they to get accurate results? And you guys did that. You guys did that quite a bit in your labs. You did that quite well. So that's one of the most important aspects of this class. Okay, so where do we go from there? We have physical quantities. We gotta get this going. That we talked about. So quantities. I want a T there. Physical quantities. So some physical quantities are measured, and some are calculated from other measurements, right? So we talked about what is measured and what isn't measured, and we found that we can measure length, we can measure mass, and we can measure time. Mostly. Okay. So we measure those three things, and from those we get all the other calculated things, right? So, for instance, our moment of inertia is equal to, I don't know, let's say 1/3 the mass of the object times the radius of the object squared. Well, we've measured the mass, we've measured the length of the radius, and those things go into this calculated thing. Well, that calculated result is also, we can also have tons of stuff like velocity, for instance, or force, or energy, or you name it. All the other things, right, that we've been coming up with. Momentum, right? That's our mass times velocity, which is really our mass times length divided by time, right? So that's our momentum. So all those things get calculated after we're able to measure these items. Now, it seems like when we're doing our labs, it seems like we're doing, we're measuring those things automatically. But what happens? our lab quest, whatever number it is, our lab quest data acquisition device. That thing is doing all the calculations for us. Does many, and you guys even learned how to make it do an extra one with the omega squared. I'll put I don't want that in there. Where'd it come from? Yeah. I'm going to just write omega squared here because you guys did it. It does calculations based on measured quantities or length, mass, and time. You guys went through and programmed omega squared into the lab quest so you could graph your force versus omega squared, and then that it was for the centripetal lab, and you were able to get some force versus omega squared graph, and then it had a slope, and you were able to go through and do all the rest. So those are very helpful. The lab quest is very helpful, but still the only things that were actually measured are those things, and then everything else is calculated from it. Okay, good. So we talked about units and different types of units, and what are we dealing with when we are saying units. We're dealing with the SI system. It's the System Internationale. And of course, we do meters, kilograms, and seconds for those measured quantities. Okay? All right. Well, everything else comes from those. And we started naming things, right? Like, let's see, a kilogram meter per second squared. So we figured out what that was. That is an acceleration times a mass. And if we have acceleration times mass, what do we have? We have a force, and what are those in? Newtons. So 1 Newton is equal to 1 kilogram per 1 meter per 1 second squared. And we name these things typically after people, right? This is 1 Newton, because their contributions to physics was large enough or pertinent enough to cause us to do that. Because nobody wants to go writing this all the time, right? You don't want to write kilogram meter per second squared all the time. You just write a Newton, and everybody's happy. And we all know what we're talking about. So, good. Orders of magnitude. We did talk about orders of magnitude, and I think you guys did well with that. So we're not going to really do much more with orders of magnitude. I shouldn't say that. We will be doing orders of magnitude. I'll talk about that in a second. What we won't be worrying a whole bunch about is significant figures. Okay, so how many digits do you carry, right, in your answer? So what I want now and forever more in this class is 3 digits. So you would have 3.45 times 10 to the 2, whatever. And then your units. Let's say they're newtons. Okay, so this is what we call scientific notation. And 3 digits is perfect. Why do we do 3 digits? We do 3 digits because if you do 4 digits, 10,000th, right? So let's say 3.4. That's the tens unit. Tens. Here's 100th, right? That's 100th. Here's 1,000th of it. And the 1,000th, we could put a 6 there. That 1,000th is a 1,000th of this, okay? And it's essentially 1 out of 1,000 is inconsequential. So when we get to this point, it's just too small to be consequential, especially for our class. So we aren't using this digit. We're just going to cut it out. We're going to use the scientific notation and just keep our 3 digits because 1,000th is too small to worry about for our sake, and for just about anybody else's sake in the world as well. I don't know why people care about those things at all anyway, but I'm trying to erase this little guy over here. Okay, got it. Okay, so let's get back to orders of magnitude. That's the thing that I really want to talk about at the moment. Orders of magnitude. So let's deal with our 3.45 times 10 to the 2. And let's say we have that measurement, but we also measured 6, 7, 8, but times 10 to the 0, which would be just times nothing. So we could say this is newtons, we could say this is newtons. How many more orders of magnitude is the first one over the second? Well, order of magnitude is 2. So this one is 2 orders of magnitude larger than this one. Okay, so orders of magnitude. Where does the 2 come from? It comes from right there. What is an order of magnitude? That is just 10 to the whatever. So if you have 10 to the 0, you're dealing with this. If you have 10 to the 1, you're dealing with 67.8. If you're dealing with 10 to the 2, you're dealing with 678. If you're dealing with 10 to the 3, you're dealing with 6,780. That kind of thing is an order of magnitude. How much larger is this order of magnitude than this order of magnitude? It's 3, because you take 3 and you subtract 0 and you have 3. So that is orders of magnitude. Okay. Sorry about that, everyone. Units and conversions, that's one of the hardest things. I know you guys are pretty good at it at this point, but I also know that you guys aren't great at it. But units and conversions, so if you have a certain type of unit and you need to convert it to something else, you typically want to put everything in an SI unit, right? So you're looking for the meter, you're looking for the kilogram, and you're looking for the second. But also in SI, we have our newtons, we have joules. There's all kinds of other ones, pascals for a newton times an area, divided by an area. I'm sorry, newton divided by an area. So units and conversions, these are what you're looking for, and you probably should convert everything into one of those SI units so that you can do your work. And one of the units that people are having seem to be having trouble with would be, say, omega with radians per second, or alpha with radians per second squared, right? That is omega and that is alpha. And so, you got to get your conversions. And one of the hardest, or one of the most common things, is revolutions per minute. Revs per minute is a better way to write it. And then you can convert that revolutions per minute to your SI unit, because you can say, well, one revolution, and I put it down in the bottom so I can cancel it, is equal to 2 pi radians, right? We don't want degrees, we want radians. So we're going to turn it to 2 pi radians, so that's one thing to do. And then I have to put the 1 minute on top, so I can cancel out my 1 minute, and I can divide by my 60 seconds. And now, what am I left with? I'm left with radians per second. So that is just an example of a conversion, one of the most common ones that happen. You guys can do centimeters per second. You can convert that, right? Because you can convert your meters. You just do your 0.01 meter per second, right? So you guys can do a lot of them pretty well, but I don't think they call it the train track method anymore, but you've got the two tracks, you've got the numerator and you've got the denominator, and you just need to be able to cancel them out so that you're left with one thing or the other. That's the way I do it, and that's just, I don't know. As far as I know, that's how everybody does it, but there are really smart people out there that are able to just drop those things pretty easily. They can just see it. I don't know how. I don't know what they do. So I have to write it out every time. I have crazy ones that I work with that I try not even to think about. Okay, forget about that. All right, let's do some trigonometry. And we're into this already about, 10 minutes? So set timer for 45 minutes. And trigonometry, let's do some of that. It comes anytime you guys can do a nice triangle, do it. Okay, so you have your nice triangle, you have your angle here. I'm going to put a different angle up here. So here I have theta down at the left, and then on the right up top I have phi, or phi, or whatever people want to call it. I call it phi. Of course, we have our hypotenuse here. Here we have our opposite side of theta, and here we have the adjacent side of theta. Okay, so if we wanted to do things like find the sine of theta, we can do that by taking the opposite length and divide it by the hypotenuse. We can also do the cosine, and that would be the adjacent side divided by the hypotenuse. And then, of course, the tangent, which we use quite a lot of, right? You didn't think you'd use the tangent as much as you do, but you do. Tangent is probably one of the ones that we used, I wouldn't say the most, but it was equally used as the others. And that's just our opposite over our adjacent. We can then say things like theta is equal to the arc sine. That's not the arc sine. The arc sine of the opposite over the hypotenuse. Okay, so what are we talking about? The opposite is a length, right? Or if this is a force, it would be a force. It doesn't matter, but it's the magnitude of this vector. That's what we're talking about. So you're taking that magnitude and you're substituting it in anytime you see the opposite side or the adjacent side. That's just a magnitude. Or the hypotenuse, same thing, right? And we're getting this length is equivalent to the actual magnitude of the thing. And you're taking those and you're substituting in the magnitudes in the different places. So we've got theta is equal to the arc cosine of the adjacent side over the hypotenuse. And lastly, we've got the arctangent. And the arctangent, so here I'm going to put adjacent. So what we're doing when we do the tangent is we're doing it with respect to whatever this bottom one is. So with respect to the adjacent side. So we're getting this angle because we're taking it at 0 at the adjacent side and we're going with respect to that adjacent side. If we were to flip those and put the adjacent over the opposite, what we'd have is phi, because we'd be doing the arctangent of the adjacent over the opposite. So that would be with respect to the opposite side. So we would be getting this angle, or this angle. So it all comes down to how you're laying out your coordinates. So, okay, all right. And of course you can do phi. For phi, this all of a sudden becomes the opposite side. This becomes the adjacent side. That's still your hypotenuse. That doesn't go away. And phi gives you that other angle. Everything with respect to that other angle. And that's it. That's trigonometry. That's that is the extent of the trigonometry that you really need to know. And from there, you can just do everything. Okay, oh, don't want that. Let's try this again. So let's talk a little bit about vectors and such. So we have I'm going to call this my x-axis. I'm going to call this my y-axis. And I'm going to draw two vectors. Okay, so I'm doing exactly from the book or from my notes. So here's my v vector. And over here is my u vector. All right, and we can do some stuff, right? We can add them. So let's add the two vectors. So we're going to take v and we're going to add u to it. And what I would do is I would pick up u and I would put it head to tail like that. So that's my u vector. I've just picked it up. I put it the tail of the u on the head of the v, and that's going to give me my resultant. Okay, that's the head to tail method. Okay, now if I want to add or subtract, I can do the same thing, only when I subtract, I'm taking v, and I'm going to subtract u. Oh, well, what the heck? What am I doing? That's going to be my new, I'll call it this one r plus and this one r minus. That's my new vector, r minus. But what am I really doing? I am taking a v, I'm adding a negative u to it. All right, that gives me my r negative. So if I'm going to add a negative u to it, I'm going to take this away. And I'm going to say, well, a negative u is going to point this direction. I'm going to pick up that negative u. So that's negative u. I'm going to pick it up and I'm going to bring it over here. And now I have my resultant to this point. So it totally changed, right? The resultant is definitely different. And that is my r minus resultant. All right, we'll make it this color. That's our resultant. I hope that's green, but if it's not, it doesn't look green. But then again, I don't know. Okay, whatever color that was, that's fine. I'm going to do a different color from now on for that color. All right, so anyway, I think you guys get the point. One of them, our plus u, went this direction and gave us this resultant. That would be our r plus. Okay, so we have an r plus, we have an r minus, and I'm just naming them this way so that you guys can see one is a plus, adding them together, and one is subtracting them. Okay. That's head to tail method. What's next? Okay, let's break down some of these. Break it down. Let's break down some of these vectors. I want to erase. Oh, I want to erase all of that. I don't want this anymore. And I don't want this anymore. I have the two vectors. And oh, that's so good. What a straight line that is. Okay, nice. So there's my two vectors. Let's break them down. All right, so we can break these down and do it in an analytical way so that when we actually want to add and subtract these things together and get real answers, what we're going to really do is we're going to have our R plus is equal to V plus U, but that really entails Vx plus Ux, and that's in the x direction, and then we're going to add in our, think of this as like a big plus sign. Then we're going to, because this is equal to Rx, then we're going to add in our Vy plus our Uy, and we can think of that as our y. So those two things will be added together. Those additions will give us our actual answers. So we have to figure out what Ux and Uy are. So here we come down over here. What did I call it? I called this one theta, and I called this one phi. So we can do that. If we know V, so V magnitude is known. All right? But we really want Vy. And we really want Vx. So V is known, right? And we know that Vy, from before, up above, we said that Vy is equal to the magnitude of V times the sine of theta. So that'll give us our Vy. We can get our Vx similar way. Vx is equal to the magnitude of V times the cosine of theta. And those are numbers, right? You have a number when you're done with that. And you can put those numbers into their specific places. And the same thing goes with Ux. That's going to be the magnitude of U times the, we're doing x, so we're going to do the cosine of not theta, phi. And then Uy would be the magnitude of U times the sine of y, phi. All right, so great. Let's draw in this little guy here. That's our opposite side, so that's our Uy. This is our adjacent side, so that's our Ux. Now, what is really happening here? Ux, we can all say, is negative, right? So we could do this the way that it is, and we have to supply a negative number to it. Okay, we know on our graph, we know that this over here is the negative side. We know that this down here is the negative side. So we know that Ux points and is negative. So I can do this calculation and then slap a negative on it, and then I have some negative number when I do it. For the Uy, I don't need to put a negative because I know it's pointing up in the positive direction. So then I just get some number. Okay, this would be the x number, this would be the y number. Or we could take from the positive x-axis and figure out what this, we could call it phi 2. Okay, what is phi 2? And if you put in phi 2 here, so let's, I'm erasing there, and I'm going to put in phi 2. If I put phi 2 in there, that's actually going to give me a negative number because I'm going all the way from the x-axis to where my vector is pointing. So that really would give me a negative number, but either way, I need to have a negative for that ux. Okay, so I've noticed a few of you guys are missing those little subtleties, pointing in the different directions, positive and negative. That's why it's so important to define your coordinate system. Once you've defined your coordinate system, all the vectors are either negative or positive according to your coordinate system. Okay? So it's essential, it's crucial for you to do those things properly, and you will get the right answer whether you've defined it one way or the other. It doesn't matter. You'll always get the right answer. It just might be a little bit more difficult one way or the other. So we've done additions, we've done subtractions, we've broken down a vector. Let's add a vector together and figure out some stuff. So we're going to be dealing with r plus here. I'm going to deal with this one. So let's slide up, get a little room here. Let's deal with r plus. We want to know the magnitude of r plus. So that's a question. But what also is a question is, what angle for r plus? Okay, what's our angle for r plus? So how do we do that? Well, the magnitude, and if you guys aren't screaming Pythagorean theorem right now, you should be. So we're going to get the magnitude because we have taken Vx and Ux, we've added them together. We've gotten Rx when we did. We're going to square Rx. All right. And we're also going to square Ry. So we've added Vy and Uy together. We're going to square that. And we put them together, we add them, and then we take the square root, right? Pythagorean theorem. That is not how you spell Pythagorean theorem. Okay, great. So we apply the Pythagorean theorem. Now, just as before, this is a vector just like any other vector. And if you want theta r plus, you're going to do the tangent, the arctangent, of rx over ry or ry over rx. It all depends on what angle and what do you want it with respect to. All right, so I'm going to suggest that you put ry over rx just because that seems to be the right thing to do just about every time, because we want with respect to the x-axis, typically, okay? But if you label something and you're saying this is the angle and I want this to be the angle that I'm doing it with respect to, then just, that's fine, just do it and just make sure you're consistent, okay? So you can do it however you'd like. I'll look for the consistencies, and if they're there, then great. If they're not, if you flipped it around or whatever, then, you know, you lose a point, whatever. Okay, so with respect to the x-axis, in this case, because we've got this in the denominator, what does a vector need? What do you need to have a complete vector? So on the test, if I say I want, please give the vector, I want the whole vector. I don't want just the magnitude, right? I need the magnitude of the vector, but I also need the angle that it's at, okay? And you are going to tell me the angle, and you're going to tell me with respect to whichever axis. You're going to say it's with respect to the y-axis or the x-axis. or the negative y-axis, or the negative x-axis, okay? So you're going to say what it's with respect to, okay? That theta. And I'll go, oh, yeah, that's true. Okay, all right. So I'll say, good job, nice work. All right, so we just talked about vectors, but part of what's happening in physics is knowing whether something is a scalar or a vector. All right, so is it a scalar, is it a vector? We don't know. Sometimes we're asked, or we have to figure it out, or we just know that it is, right? So the difference, one of the things is speed. This is the one I like to use as an example, speed and velocity. Because the V's match and the S's match, right? Speed is a scalar. It doesn't care where you're going or what direction. It just wants to know the magnitude. Doesn't care about if you're going north on I-25 or south on I-25, when you're saying I'm going 75 miles an hour on I-25, nobody knows if you're going north or south. You're just going 75 miles an hour, right? So keep up the good work. Velocity, however, is your magnitude plus your direction. Okay, so I'm going north 75 miles per hour. That tells me the direction and the magnitude. And that's what we're looking for when we're dealing with a vector. Okay, so one is, it's a good circle, just didn't have that in the center. One is just your speed, more like a radius. It could be pointing in any direction. Okay, so that's your speed. We don't care which direction it's going. It's willy-nilly all over town. And then one is a specific vector that is your velocity. And it does have a direction, and you would say with respect to the x-axis or whatever. Okay, now you definitely have a vector. Okay, speed would just be a radius or a magnitude. V is your vector. Why did we call it a scalar? Because if you have a resultant vector, that resultant vector might be equal to, let's call it S, or S times some other vector, U. We could have U pointing like this. We've got some speed multiplied by this U vector. What is it doing? It's scaling S times U. If S is larger than 1, then U grows, or S times U grows. If it's less than 1, then it shrinks. So it all depends on this. Why? So what have I just done? I have scaled it. I have U, and it's been scaled. It's either been increased in scale or decreased in scale, depending on whether S is greater than or less than 1. And that is the whole point of calling it a scalar. Our S is a scalar. It scales it up or down. That's why it's called a scalar. Vectors, just it's pointing in a certain direction with a magnitude. I don't know how else to say it. That's a vector. There's no rhyme or reason there. They just named it a vector, and that's it. It's probably Latin for something somewhere. What types of things are scalars and what types of things are vectors? Mass is a scalar. It doesn't point in any direction. It's just a value that something has. Time does point in a direction. We're not going to talk about that. We're just going to say time is a scalar. Speed. We just talked about speed. great example. And then just straight up distance, because you've traveled a certain amount of distance, but we don't care which direction. So distance, these are all scalars. And then on the vector side of it, we have our velocity. We've got acceleration. We've got delta x. That is a vector. We've got p. That is a vector. We've got delta p, our impulse vector. And force, one of the most important vectors there are out there. But nicely, joules, or energy, is a scalar. And a torque, believe it or not, torque is a vector. Moment of inertia is a scalar. Yeah, let's just leave it like that. Vectors versus scalars. I think you get it. I'm not gonna go into it anymore. That's it. That's scalar vector stuff. Okay. In the notes, I put some stuff about your average velocity, which is a vector. So we have our average velocity, and that's equal to delta x, which is a vector, over time, or we could say delta t. So it's your average velocity. It's pointing in a direction. Now, if you want to just make it the average velocity, like this, then you take the absolute value right? The magnitude only, and now you have literally just the magnitude of that vector. And many times that's all you really need to know, right? So it all depends on if they're asking for a magnitude or the vector itself. Acceleration vector. I'm just really gonna, real quick, I'm gonna say mass is our scalar, acceleration is our vector. This vector points in a certain direction. It must be the same direction as this one, okay? They have to be equal because they're the only things that are vectors. So this vector and this vector to be equal, for this equation to be equal, that they have to point in the same direction, okay? All this does is scale. All right, it just scales it. It makes it bigger or littler depending on how big m is, okay? So magnitude-wise. Okay, let's move on. We're on page 4 in the notes, if you're keeping track. We've got the acceleration of gravity. So I'm just going to draw a nice projectile motion. We've got the top. We have some initial velocity there. And it's a poor, let's get rid of that. And there's our initial velocity. All the time, gravity is acting down. Okay, so gravity is our acceleration, and it's pointing in this direction. Okay, we don't have any acceleration, so that's all AY. AX is equal to 0 when we're dealing with projectile motion. Okay, so gravity is pulling it down. At the top, we're going to have Vy is equal to 0. This is V naught x, this is V naught y. and this one is V naught. V naught x never has an acceleration, so V naught x at all points is going to be the same length. Okay, it always wants to go that fast because our momentum in that direction is equal to whatever the mass of the object is times our velocity in that direction. And that momentum is never going to change, right? Our px initially is equal to our px finally. And it's all the same, the mass of the object times the vx, okay? That is conservation of momentum. Okay. Of course, we start out over here with some large V naught y. We get to V top, which is 0 in the y direction, and then gradually the acceleration spits back out V final in the y. Okay, so okay, that's projectile motion. Now, depending on whether you've named up or down as positive, this is either positive or negative. It all depends on what you've done. What have you done? Okay. Let's talk a little bit about our equations of motion. You guys should have this pretty well nailed down. So we have x equals vt, right? That's the simplest thing. Or you could say that your velocity is equal to, or speed, is equal to your distance divided by time, or length divided by time, or however you want to do it. That's fine, but what are we really saying? Technically, we're saying our average velocity is equal to the distance x, delta x, divided by delta t. We can also say that our x final is equal to our x initial plus our average velocity times time. And this, again, is the same equation, okay? It's the same equation. All I have to do is do x final minus x initial. That equals my velocity times time. And we know that this bit right here is equal to delta x. So now I've got delta x divided by time is equal to my velocity. And I just showed 3 steps to get back to this equation. All right? And, delta t initial is always 0, so whatever, but okay. Fine, we've got that going for us, but let's do a couple others. We want to add in a few other things. Our acceleration is equal to our delta v, not delta x, over delta t. So what does that mean? That means that we're doing delta x over delta t squared, right? Not quite. I can't say that. I'm not going to say that because that's gross. Okay. You still have to know what delta v is. So you have to know what v final is. To get delta v, you have to know what v initial is to get delta v. And once you know those things, then you can substitute in that for this. And you can do that. Okay, but let's put down a couple other equations. X final equals x initial plus v naught times time plus 1/2 our acceleration times time squared. So that's 1, and there's a lot of ways to write that. You can write it as delta x is equal to v naught t, because what are you asked for? Typically, you're asked for one of these things. They'll ask you for this, and then they'll have to supply everything else. Or they'll ask you for this, and then they'll have to supply you with everything else. Sometimes they'll ask you for this, or sometimes they'll ask you for the time. So it all depends, okay? But this is a very fundamental equation that will be used. So there's that. There's also the third equation, or fourth, depends on how you look at it, where v final squared is equal to v initial squared plus 2ax. I want to talk about this one a little bit because it goes into v final squared minus v initial squared is equal to 2ax. This goes into your kinetic energy. So if you have delta KE and it's all linear, okay, you're not dealing with rotations, you can do your delta KE as 1/2 your mass. The mass doesn't change, but v final minus v initial are there. Well, that's nice because you can now slip in your 2ax for those two things if that's what you know. If it's not what you know, then of course you don't want to do that, but that's a very, very useful thing. Okay. Useful little notion. Falling objects depends on the height that you're at. So gravity, let's draw an Earth here. But let's put a satellite way up outside in Earth. The gravity at this point would be, let's say that's radius of satellite. That's equal to the mass of the Earth divided by the radius of the satellite squared times g. Okay, so that's g for the satellite. And that's not the same as g on the surface of the Earth, okay? Because this is the radius of the Earth. That's totally different. So our g for Earth would be at the surface of the Earth. That would be the mass of the Earth divided by the radius of the Earth squared times g. These are two different things, okay? So g changes depending on how high you are or how far away from the center of the Earth you are. And that also means that you can do it on different planets, right? So we can have the moon. Draw some dots on the moon. Something like that. The g on the moon, g moon, is very much less than g Earth because the moon has a lot less mass and it has a smaller radius and all of that. So in each of these places, we have a projectile motion happening, and we can think of that projectile motion as being a constant. So we can come down here and we can say, okay, instead of dealing with a round Earth, locally we're dealing with a flat Earth, and maybe we have how much time do we have left? Oh, 5 minutes. Maybe we have a thing that is getting launched with a certain v naught x, and then gradually it's going to get pulled faster and faster and faster down to here. that happens, but we would assume that G is constant throughout that entire fall H. Okay? It's going to accelerate down because the only acceleration is in this direction. All right? We can call that positive if we want. We can call it negative, whatever. Now, if we have an initial v naught y equals to 0, which in this case we do, and we want to know what v final is, what we really need to do is we use that equation, v final squared is equal to v initial, but v initial is 0. So I'm just going to say 2 times my acceleration times my height, because height is my distance that I traveled. Easy, right? This equation makes this whole thing easy, and we don't need to figure out what the time is. However, there is a certain amount of time that it takes for this thing to go from the top to the bottom. If you're dying to know what that time is, you can do that by noting v final is equal to your acceleration times time, or acceleration times time. However you want to think about it. In a gravitational situation, your acceleration is g. So you can do that, but you have to know the time. Or if you do figure out what v final is, you can now get the time because you know what your acceleration is, and you now have how much time it took. So we can solve for time now and get our v final divided by g is equal to the amount of time that we had. Okay, we're on page 5. I have in my notes that this is a good time to take a break, so I'm gonna move up, and we're gonna start fresh at this point. So let's stop.